morning. This is Dr. Ravi Kant here. I am a faculty in mechanical engineering at Pandit Deendayal Energy University, Gandhinagar, Gujarat. The work is namely is optimal perturbation control in plane Poiseuille flow using stability modifier. To start with, the aim of this particular talk is all about the separation of perturbation evolution in a simple channel flow. So let's start with the flow setup. So these are my assumptions. So we are going to limit ourselves in numerical simulations only. And this is let's suppose this is a plane channel. A flow is happening. It is having disturbance velocities u dash v dash w dash. And another assumption we would take is we will be limiting ourselves in local stability framework. That is, we are going to judge, or we are going to simulate the parameters on one particular y location, one particular x location in y direction only. And we assume that this domain is periodic in x and z. So in a way, it's we are going to assess only stability, local stability. We are going to limit ourselves into local stability framework only. The periodic domain is in streamwise x and spanwise z direction. Okay, and disturbance are assumed to be of wave-like nature, and which is having certain wave number alpha and beta. And the Wall transpiration that we are going to input is also at the same wave numbers that are present, and which is taken into consideration. And the same wave number pair jet actuation must be supplied in order to attenuate that particular disturbance. So to start with linear stability, linear stability is all about taking the base flow solution, which is satisfied by Navier-Stokes equation. Also, the instantaneous Navier-Stokes instantaneous flow is also satisfies Navier-Stokes equation, so which is nothing but the base flow plus the perturbation. And once we subtract it from this particular these two things, once we subtract it, we get these equations, these vector equations, 3 momentum and 1 continuity in terms of dashed variables. So I didn't talk about what these dashed variables are. The disturbance variables, and these capital variables are the base flow variables. Okay, so in order to make a proper mathematical model, we are going to eliminate the pressure terms, the disturbance pressure terms, and we are going to write solely everything in y direction or wall normal perturbation, and another variable we define as eta variable, eta dash variable, which is the wall normal vorticity. So there are two equations. This one is first equation, second equation, and it has proper boundary conditions with it. So that is no slip and clamped condition at walls, and similarly normal vorticity also has no slip at wall. So these two equations, we have these two equations with us, and then what we do is we will go by normal mode analysis. So this is feasible once we have assumed that we are going to limit ourselves into linear regime only. Then only this normal mode analysis is feasible. And once we assume that, we we also assume that your disturbances are a sinusoidal kind of function, and which has this this amplitude, which is a function of y and t only, and that is the basis of your local stability approach. And also wall normal vorticity is having this much amplitude with the function y and t, and this is the sinusoidal component, these two. Okay, and this amplitude is also going to be estimated by this function. Okay, by some coefficient, some unknown coefficient plus some Chebyshev basis polynomials. Okay, and these unknown coefficients, which are a function of time, is essentially will take the state vector for your state space equation. So so the idea behind all these things is to construct a state space model uh, to get the proper uh, control framework. And this is the Chebyshev basis function. This is again these two are unknown coefficients which takes up the state equations in the state space model. Okay, so now we have already summed up our all the assumptions. Now what we will do is uh, we will substitute these equations into these two equations, uh, v dash and eta dash equations, and then we write these two particular equations. One is this one and another is this one. Notice that capital U's are the base flow solutions that we already have a priori through the uh, mean flow equations. That is our parabolic. U is nothing but your parabolic solution, and which we know a priori. Okay, and we are going to substitute it here. But for numerical simulation, we have to write these equations at all all the nodes. Okay, so you need to essentially you have to discretize it. So we are going to discretize in uh, Chebyshev fashion. So it is in a way it is more accurate and uh, more precise in terms of solution, because it is more condensed in the boundaries, and which is also a necessary part to judge the performance or judge the stability of a domain, flow domain, control features into it. Mathematically, how would you do that? So you start with certain uh, you assume that you are going to input certain uh, jet velocity in y direction, and that you are going to start with some q variable, which is also assumed in same fashion what you have assumed for your disturbances. But the thing is, your wall normal velocity is going to be modified. So this was your previous assumption, but you are going to modify it with this particular guy over here. Okay, you tell that this is my extra additional velocity that I'm going to put as my control input, and which is also known as forcing function, and which also can be written as a separation of variable as fuy and qut, fly, qlt. So u subscript means upper wall and L means lower wall actuations. So in a way, this qt is going to be decided by your controller. Okay, and these two things are um, standard functions you can take, and this qt and ql would be decided by your controller, and that is the uh, control challenge that we are going to have here. So what we see that there is a transient jump in the system, and that may also lead to transition. So we are going to look for these jumps, and we are trying to suppress this also by some control means. Okay, so before going into the results, we also have validated our stability results first from this paper. At this particular Reynolds numbers, we have already validated our results for the growth functions with time. Okay, now once we have validated our result at Reynolds number 8000 at particular alpha and beta values, alpha 1, beta 0. Once we have applied the control, we can see the peaks has been attenuated sufficiently. Optimal growth functions. So this is at one particular alpha and beta. Okay, so what we have done is we have a spectrum of alphas and betas. So we vary alpha and beta. Okay, so we vary alpha and beta. Sorry, not alpha and beta. We kept our beta 0 constant, but we varied our alpha, and we've also varied our Reynolds number, and based on this we have a Gmax contour for each location. We can see there is a Gmax that is prominent over in this region, and once we apply control, we can see that there is a shift in uh, the highest Gmax value. Okay, so it is no more there uh, in your desired region, so it has been limited. Uh, this is the way to judge your uh, stability situations as well. We also have plotted U dash contours. So stream-wise perturbation field is also plotted at Reynolds number 8000 with alpha 1 and beta 0. And we can see at one particular, so essentially this is your flow. So at one particular x location, I'm going to plot this. This is +1. This is from -1. So we have this perturbation control with time. Okay, so we can see with no control, the perturbations are happening in wave-like sinusoidal wave-like nature. We have an animation also in the next subsequent next slide, and we can see with single boundary control, we have suppressed our Gmax sufficiently, and with this is for both boundary control, suppression is much better in this case. So this is the no control case. You can see no control case, the streamwise perturbation animation at all the times at one particular y location. You can see once we have applied the control, now you can see the attenuation has been done appropriately. Similarly, the wall normal contours, perturbation contours are also plotted at Reynolds number 8000 and alpha 1 beta 0. And with no control case, you can see how the perturbation is sinusoidally increasing as well. And with single boundary control, you can see only down boundary is giving some sort of perturbation. I mean, some sort of wall actuation. It is evident here also, and you can see the wall normal perturbation. The actuation is done from the walls, and you can see the with time the things have been damped out. The wall normal perturbation has been damped out. It is also evident in this animation with no control. Wall normal perturbation is happening, and subsequently it is going larger and larger. Once the combined both boundary control has been applied, it has been suppressed. So in conclusion, I could say that we have studied the comparative effort of stability modifier to control the instability waves in plane Poiseuille flow in order to mitigate the temporal growth of instabilities. We did the jet actuation and in the frame of in the framework of LQR control framework. And after that, once the feedback is done, we have found that the Gmax has been attenuated sufficiently. As a future work, we can also, so this work has been done locally in local stability framework. We can also go for global stability approach and control. Thank you. Any question?